Hi friends, in this video we'll discuss about inductance. Inductance is of two types, self-inductance and mutual inductance. We'll discuss both. Consider a solenoid. If I pass a current I through it, what will be the flux through each loop? Say it is phi b. And for n loops, it will be n into phi b. And note that this flux will be proportional to the current which we pass. More the current, more will be the flux. So this term n phi b is known as flux linkage and it is proportional to current, right? So to remove this proportionality, I'll have to introduce a constant. Let it be L. Actually, L is known as inductance and it depends on the geometry of solenoid. It is a scalar and it's named after the scientist Joseph Henry. If I pass a variable current, I mean the current which varies with time, then what happens? EMF induces in each loop. Why? Because magnetic field changes, right? And change in magnetic flux induces EMF, you know that. So EMF induced in all the loops will be minus n into change in flux d by dt of b dot a. That is nothing but flux, right? This is by Faraday's law. Now I want to calculate this minus n and d by dt of what? Magnetic flux here is mu naught ni, small n, number of turns per unit length, and current is I. Area is pi r square. Say it is capital R. Now mu naught is constant, number of turns per unit length is constant, and radius of solenoid is fixed. So current is the only variable here. I can write the same EMF induced as minus n mu naught n pi r square. All these are constants, and here I have di by dt. Okay. Hope everything is clear till now. Observe this. Take this equation. Flux linkage is nothing but L times I. So flux linkage is equal to Li. Okay. I'll derivate this equation with time d by dt, and here also I'll do d by dt. And what I'll get? Minus E by Faraday's law, the rate of change of flux UCMF, right? This is equal to L is a constant and di by dt. Hope this is clear. So from this we'll get E is equal to minus L di by dt. Observe this. This is the EMF induced, and here by following another method we got this as the EMF induced. So from these two equations, what can we infer? Both are of same nature, right? See, here you have di by dt, and here you have E and T, and both have negative sign also. So from these two, what I can say, L is equal to mu naught small n pi r square capital N. Okay, I'll write again. L is equal to mu naught small n capital N pi r square. This is the inductance. As I said before, it depends on the geometry, and I can write it in another form as mu naught n square capital N square pi r square by, because capital N is the total number of turns and L is the length of the solenoid. And note that when you increase the length of the solenoid, the inductance increases. So here you have length in denominator. So if you increase the length, it appears that the inductance decreases, but actually it is not. You have this capital N here, which is the total number of turns. So if you increase the length, the total number of length increases, the total number of turns increases. So if you increase the length, the denominator increases, but the numerator increases even more. Or I'll better write this equation in another form. Mu naught n square pi r square into L. This will do it, because mu naught is constant, number of turns per unit length is also constant, and here you have L. So as the length increases, the inductance also increases. Hope everything is clear till now. The unit of inductance is Henry. I'll explain you. Di by dt, right? So what can the units of L be? L is volts, and here you have change in current amperes by change in time. So volts per ampere per second. And physically, the self-inductance plays the role of inertia. I'll tell you. Observe these formulas. F is equal to mass into acceleration, right? And observe this formula. EMF is given by this one. Don't you feel they are similar? Here, m is what? M is mass. That is, mass is the measure of inertia. Inertia is something, a property which tries to oppose the change in velocity, change in state. So more the mass, more will be the resistance to change in the state, change in velocity. Similarly, if more is the inductance, more will be the resistance to change in electricity. Inductance is nothing but the electromagnetic analog of mass in mechanics. I want to build current I in a solenoid, and what is the energy I have to spend? Okay, you know that the power is given by potential drop into current. Okay, here say E into I. This is the power, right, which is nothing but rate of work done. Now I know that E is given by L into di by dt, and here you have I. So if I cancel this dt and dt, what I'll get? D omega is nothing but Li di. I'll integrate on both sides, and finally I'll get the work to be half Li square. And note that when you have a mass m and the energy that you need to spend to give a velocity v to that mass is nothing but kinetic energy, half mv square. And here the energy that you need to spend to give a current to a solenoid is half Li square. Again, note the analogy. This energy, this magnetic energy is stored inside the solenoid. So I want to calculate it. What is the L? It is mu naught n square Al, where A is the area. And what is I? B by mu naught n, because B is the magnetic field which is given by mu naught n I. So I can write this as half mu naught B square and Al. This is the total energy stored inside the solenoid. So what will be the energy stored per unit volume? So that will be this energy divided by volume, right? Volume is what? Al. So Al gets cancelled, and finally I have half mu naught B square. This is the energy or magnetic energy stored inside a solenoid per unit volume. And in electrostatics, we calculated the electrostatic energy stored inside a parallel plate capacitor per unit volume as half epsilon naught capital E square, where capital E is the electric field. Again, you note the analogy between these two formulas. Magnetic field is replaced with electric field, and wherever you have 1 by mu naught, you have to put epsilon naught. That's it. Let's move forward. The next topic is mutual inductance. When you have two coils, two solenoids placed nearby, and when you pass a variable current through one, what happens? Magnetic field changes in the other coil also. So EMF is induced in the other coil due to the change in magnetic flux, and this phenomenon is known as mutual inductance. Say I have a coil here and another coil here which is placed nearby, and note that first coil has some bigger radius, say capital R, and let the radius of this be smaller. First I'll pass current through the second coil, variable current, let it be I2, and because of that I'll get some EMF induced in the first coil, and flux linkage in the first coil will be N1 pi 1, which will be proportional to this current, because now current is flowing in the second coil, right? So more the current, more will be the flux. And to remove this proportionality, I'll introduce a constant which is M, actually M12. It is the coefficient of mutual induction, or you can say mutual inductance of solenoid 1 with respect to solenoid 2. This is how you read it. And let's solve this. N1 phi 1 is what? N1 is the total number of turns in first solenoid, that is small n1 into length. Say both the solenoids are having same length, and here for phi 1 what you will do? Phi 1 is the magnetic flux in the first coil, right? And magnetic field lines are given due to the second coil. Note that, because current is here. What will it be? Observe this. I'm seeing it from here. This will be the first coil and this will be the second coil. Of course, magnetic field lines are given because of this smaller coil, but they pass only through this area, through the smaller area. You notice this part, all this part is free of magnetic field lines. So the flux also is calculated only by using the smaller area for the bigger loop also. Are you getting me? While calculating magnetic flux, what did I say? The total flux B dot A is given by B1 dA1 plus B2 dA2, where dA1 and dA2 are the smaller parts. So what can we say here? Divide this bigger loop into two parts. One is the smaller circle area and other is the remaining one. In the smaller circle area, you have this magnetic field of what? Mu naught N2 I2 given by the what? Given by the second solenoid. And the area is pi small r square, smaller area. And for the other part, for this part, there is no magnetic field, so hence there is no magnetic flux. So this is the magnetic flux or magnetic flux linkage. I can write this as mu naught small n1 small n2 pi small r square and what else, capital length. That's it. Okay, so observe this equation and observe this equation. On the LHS you have capital N1 pi 1. Here you have something else. So by these two equations you can say that M12 mutual inductance of 1 with respect to 2 is mu naught N1 N2 pi small r square L. Observe this small r. Now I'll pass current through the first solenoid, and because of that I'll get EMF induced in the second solenoid. So flux linkage of second solenoid will be N2 phi 2, and you have different constant, say mu 21, and here you have I1. So solving in a similar manner, here N2 is nothing but N2L, capital N2 is nothing but small n2 into L, and flux 2 is what? The area anyways is pi smaller square only here also, because the flux is through the second solenoid which is smaller in area. So we have pi smaller square, and flux is due to the first, right? So mu naught N1 I1. Again, by comparing these two equations, we have I1 here, and the remaining terms are M21, right? M21 is also found to be mu naught N1 N2 pi small r square L. Interesting, right? What can we say from this and the above thing, what we did? M21 is equal to M12. Let it be M, say. If a material of non-zero magnetic moment was placed inside these solenoids, then what happens? Just instead of mu naught, you have to write mu r mu naught. Even for the self-inductance case, if both the solenoids were of same radius, same area, then anyways this r will be the same. So it doesn't matter. Now, observe this one. If two inductors are placed side by side very near and current passes through both of them, then what happens? The N1 phi 1, the flux linkage of first one, will be given by M11 I1. So it depends on the first solenoid because current passes through it, and also on this one because there is some mutual inductance, right? It depends also on the second solenoid. So from this what we can say, the induced EMF in the first one will be minus M11 di1 by dt minus M12, and here you have di2 by dt. You have to take the effect of both the solenoids, which is nothing but minus L di1 by dt, and here you have the same. Hope everything is clear till now. AC generator works on this principle where you change the magnetic flux through changing theta. Observe this. A coil is placed here and it is rotated by some external means, some mechanical energy. So simply saying, mechanical energy is converted into electrical energy in this AC generator. If you rotate the coil with the angular velocity omega, say, then what will be this? Omega is nothing but d theta by dt. Now the flux is Ba cos theta, say phi b, and the EMF induced due to this rotation will be minus n d phi b by d theta dt. This is by Faraday's law, right? So EMF is what? Minus n, b is constant, a is constant, and d by dt of cos theta, right? And this can be written as nba sine, what is theta? Theta is omega t, right? Because omega is the angular velocity, omega t, and of course here you get omega. So this will be the EMF. This is what? This is the maximum EMF that is possible. Call it T naught because sine theta varies from -1 to 1. So finally, my EMF induced will be E naught sine omega t. And that's why this is known as alternating current, because the current changes its direction periodically.